huge application of vectors is calculating directions and magnitude in space. For 2D vectors in high school, this will be the only application you need to remember. We'll always have some thing, maybe a person, maybe a vehicle, maybe an animal, and it's moving in some direction at a certain speed. Then we'll have some external force. Maybe it's wind, maybe it's a river current, I don't know. And it's affecting a different direction and magnitude from the intended direction and magnitude of the first vector, which is coming from the thing. It might be supporting it, might be hindering it. If you're a physics student, you might be inclined to isolate both of these vectors into their horizontal and vertical components and then cancel them out from there. Don't do this. Instead, on your 2D plane, you're going to want to have some point of origin. That's going to be your thing, your creature, whatever that's trying to move somewhere in some direction. You'll draw the first vector, being the magnitude and heading that the thing is intending to go. Then you can draw another arrow originating from the end of the first that is pointing in the direction of the external force. Now, the direction that you draw this vector matters. Depending on how you draw the second vector, it can make two different triangles. It is this third vector, which is the third side of the triangle, that can mean two different things in two different circumstances. In the first type, our external force vector originates at the end of the first vector and points outwards. The third vector will be the true heading and magnitude that the thing's travelling at as a result of its own force and the external force, should it not alter the course on its own but instead be affected by this external force. The second type, the external force vector, is pointing towards the end of the first vector. The third vector for the triangle, then, is the direction and magnitude our thing should travel at should it want to cancel out the external force and travel in its first intended way. In all of these cases, you should be given two vectors that you know everything about, both its bearing and its magnitude. This means you can use angle equality theorems, such as alternate angles, corresponding angles, co-interior angles, all that good stuff, to figure out the angle between the two known vectors, after you've drawn them how I've said, of course. You can then use the cosine rule to figure out the magnitude of the third side, and then use the sine rule to figure out all of the angles in between. All the maths is done there. After that, the problem solving part is getting the worded problem and interpreting it by finding the value inside the triangle that corresponds to the answer you're trying to find. For example, if I had some plane travelling, for example, 400 kilometers per hour north, and I had a wind that was blowing at 10 kilometers per hour from the east to the west, and I wanted to know how the plane was actually travelling as a result of being blown off course, I could draw the first two vectors with the external force originating at the end of the first and pointing outwards, and then that third vector we've drawn would be the magnitude, and then I can use the angle inside the triangle to figure out its bearing as well. If I were to use a second type instead, I could have the external force vector pointing towards the head of the first, and find the vector which would explain how the plane should travel, should it want to travel at 400 kilometers per hour exactly northward, by cancelling out the effects of the external wind. Ah, my old nemesis, geometric proofs with vectors. My opinion, this is the most infuriating topic in all of the vector content in high school, since I feel like I can do it, but I'm misunderstanding the assignment, which is the biggest downfall of geometric proofs. I could say that I have two vectors, and I want to prove they're parallel. How could I do this? Conventional wisdom tells you that the first vector plus the second vector should equal another vector c. If I can prove that a plus b is equal to c, then we've proven it. It's unfortunate that vector geometry is not like conventional geometry, and that no matter the directions of A and B, A plus B will always be C through our definition. We need to be very careful now, very specific. For example, we could simultaneously claim that the magnitude of this third vector C is equal to the sum of the magnitudes of the other two vectors. This would make sense only if they were parallel, because if they were any different, you know the third side of a triangle is not equal to the sum of the other two sides. It's equal to some funky value depending on which formula you're using. If we could solve for that, there would probably only be one real answer, which would be our answer and we could consider it proven. But at that point, there's an easier way to do it, and that's just to know that if one of the vectors, say A, is a scalar multiple of the other, B, then they're already parallel and we don't need to do anything else. This is because the idea of being parallel comes from the idea that they both have the same gradient, and if one's 2, 4 and the other's 1, 2, then obviously A is exactly the same as B, because that's saying that a half and 2/4 are equivalent. That is the most basic form of vector geometric proofs. In order to consider something proven, you can't just find a case where it's true. You've also got to eliminate every other false positive true case that would refute your statement. So it's kind of like an if and only if kind of thing.